Welcome back to Multivariable Calculus. This is, as always, Professor Clark. Today we're going to be talking about partial derivatives. Let's get started. So first, a couple questions. What exactly is a partial derivative? How do you compute a partial derivative? And why would we want to? Let's take that first question. So what is a derivative? Let's go back to Calc 1. Well, there was sort of three interpretations. There was sort of an algebraic or symbolic interpretation. You probably learned if your function is x squared, its derivative is 2x. And there's a geometric interpretation of the derivative. So if your function is x squared, then the slope of the tangent line to the graph of y equals x squared at the point xy is 2x, or twice the x coordinate. So the slope is twice the x coordinate. That's a geometric interpretation of the derivative. And finally, the instantaneous rate of change. If the height of an object is given by f of x equals x squared, so at a particular time x, the height is x squared, then you could say that the height is changing at a rate of 2x. So all of these things are, in some sense, the derivative. In some sense, the derivative is the sum of all these things. So what we'd like to do is have not just one or the other, but a full understanding of derivative. All right, but this was a function of one variable. So what happens if your function has more than one variable? Well, that's where partial derivatives come in. Okay, and the way we're going to handle that is similarly to where we got the derivative from. So the derivative, the definition was this limit of the slope of the secant line. Right, so this looks like a slope. You've got change in y over change in x. So it's sort of the limiting slope, and that's where you get the tangent line. And if you apply this to x squared, you can get symbolically 2x. So let's see, how would we extend this to a function of two variables? Well, what we do is actually you get two different derivatives, because you have one derivative for x and one derivative for y. So let's say you're at some point, x naught, y naught, and you want to know what the partial derivative with respect to x is at that point. You'll notice our notation here. We use this partial symbol here to indicate that the function has two independent variables, and so we're not taking a derivative with respect to one, but with respect to one of the possible derivatives. And what you do is, if you want the x derivative, you fix the y coordinate. So you notice y naught is fixed, and you are only looking at the change in the function if you vary the x coordinate. So if you vary the x a little bit, what do you get? And similarly, you can take the partial derivative with respect to y. Well, then you leave the x coordinate fixed and vary the y, take the limit, and see what you get. So this should be a slope, but what kind of a slope is it? Well, let's try to look at this graphically. So let's take some interesting function, 1 plus sine x times the square root of y. That's a multivariable function. And let's see what happens if we try to analyze this in this case. So here's my function, 1 plus sine x square root of y. Let's graph that in 3 dimensions. It looks kind of like this. All right. And we'll need some point. Okay, so there's my point there on the surface. And what we're really going to do is we're going to move the point over a little bit, and then, but only in the x direction. So one way to think of that is to fix a plane, say y, and only move within that plane. So that would be the idea of changing x only. Okay? And what happens if you intersect a plane with a surface, you get a curve. And if I remove the surface, I just get the curve. And if I look straight on, it's just a function in some sense of one variable. It's a function, here's x and here's z. So we know how to take the derivative of a function. You take the derivative and you get a tangent line, and the derivative is the slope of that tangent line. And if I move that point around, the slope will change as the point changes. If I bring the surface back in, we're just moving that point around, but only changing the x coordinate along that surface. So the partial derivative with respect to x is simply this notion of intersecting the surface with a plane where y is fixed and finding the slope of the tangent line at that point. And of course, if you want the partial derivative with respect to y, you intersect the surface with the plane where the x-coordinate is fixed. And if you do that, you'll also get a curve, but this curve will be a function of y and z. But again, we can look at that curve straight on, remove the surface, and the partial derivative with respect to y is really just the slope of the tangent line to this curve. And so any surface will have two partial derivatives, one for x, one for y, given which plane you're intersecting with. So that's sort of a geometric understanding of the partial derivative. You can also think of it as a rate of change. If you are at a point and you are only moving in the y direction, what's your instantaneous rate of change at that point? Of course, that's the slope. Or if you only move in the x direction. What's your rate of change as you move in the x direction only? So that's a graphical interpretation, and of course these are just secant lines. It's exactly what we just did, and this fixing the y0 is that notion of putting the plane. So how do you do this symbolically? Well, the partial derivative you can think of as itself as a function, because you can compute the partial derivative at every single point x0, y0. Well, if you do that over the entire domain of the function, then fx, the partial derivative with respect to x, and fy, the partial derivative with respect to y, are themselves functions on the domain, assuming the derivatives exist. So let's compute. Here's an example. We'll take the x derivative and the y derivative of this function here. So first, if we think for the x derivative, y is held constant, so we just differentiate this function here with respect to x. That'll be 9x squared y, so that's there. And now we differentiate x sine of xy, hold y constant, use the product rule, differentiate x, we'll get negative sine of xy. And differentiate the sine function, we'll get, of course, negative cosine. And we'll use the chain rule. Differentiating the x becomes a 1, so you multiply by y on the outside, and the x remains. So that's the partial derivative of f with respect to x. And if we do it for y, we hold x constant, so this is basically just a constant. Differentiate the y, we'll get 1, so that'll leave 3x cubed. And for the sine term, x is constant, x is constant. We differentiate the sine, we'll get, of course, negative cosine. Use the chain rule, we differentiate y, we get 1x, so we multiply by x, and we already have the x, that gives us x squared. So there's the partial with respect to y. We'll do another example here. Find g sub s and gt, so these are another notation for partial derivatives here for this function. Let's start with gs. So we take the partial derivative. Well, we're going to have to use the quotient rule on this. So here's the bottom times the derivative of the top. Of course, the exponential, the derivative of the exponential is just the exponential, and the chain rule just gives a 1, minus the top times the derivative of the bottom. S is our variable. You differentiate s, you just get 1, so that's just t ln of t over the square of the denominator. We can do the t partial derivative as well. So again, low times the derivative of the top minus top times the derivative of the bottom. With respect to t, we use the product rule, so we'll have s times 1 ln of t. And then if we differentiate ln of t, we'll get 1 over t times t, which is just 1, so we just get s there, of course, over the square of the denominator. So partial derivatives work well with product rule, quotient rule, chain rule, all the rules you learned in calculus. If you want, you can keep on differentiating as many times as you want, as long as the derivatives exist. So we call these higher order partial derivatives. You can define them the 10th partial derivative if you like. We'll probably stick to 1, 2, or 3 for the most part. But f(x)(x) is simply just the partial derivative of the partial derivative with respect to x. So this is itself a function. You can take its derivative with respect to x. Or you can find fxy, so you can start with the partial derivative with respect to x and then take its y derivative. Or you can start with the partial derivative with respect to y and take its x derivative, or you can take two derivatives in y like so. So let's do an example of this kind of thing. Find the second order partial derivatives for this function here. So I've already put down the x and y partials. So if we differentiate this with respect to x, we just get ln of y times y e to the x, or plus y e to the x. And differentiating this for y, we get x over y plus 1 e to the x. So now we'll compute the x derivative of this, the y derivative of this, the x derivative of this, and the y derivative of this. So let's start with fxx. There's no x's in this function, so it's roughly just constant, so that goes away when you differentiate it, and the derivative of e to the x is just e to the x, so that's the fxx. Now let's take the y partial of this function. Derivative of natural log of y is 1 over y. Differentiate y, you get 1 e to the x. We can take the x derivative of fy, so we get 1 over y here, and e to the x there. And if we take the y derivative of this function, this will become 0 because it's constant, and we'll just get negative 1x over y squared here. And you can take third and fourth and fifth order if you like as well. So here's a question. Do you notice anything here? Hopefully you notice that fxy and fyx appear to be the exact same. So you might wonder, is that just a fluke or is that always the case? Well, Clairaut's theorem says it's always the case. So assuming f is a function defined on some domain and you're at an interior point to the domain, and if these partial derivatives exist, so assuming you have fx, and fy, so you can take the second mixed partials, these are called the mixed partial derivatives. If those derivatives exist and are all continuous at that point, then the mixed partials agree at that point. So essentially, assuming the derivatives are continuous, then the mixed partial derivatives will agree everywhere in the interior of the domain. There's some technicalities on the exterior of the domain, and if the derivatives aren't continuous, you can come up with examples where this doesn't hold. But for most of the functions we deal with, this will be the case. So here's a practice question for you. Compute the fxyz and the fzyx partial derivatives for this function here. Maybe you want to pause the video and work it out for yourself, and then I'll go over the answer. All right, so the assumption here is as long as these derivatives are all existing and continuous, these should be the same. So we will only compute one of them, and the other one will actually match up. So let's try this one. Let's take the x derivative first. That just leaves us with cosine of yz squared. We take the y derivative of that. So differentiate cosine, you get negative sine of the inside. Use the chain rule, you end up multiplying by z squared because y goes to 1. Now we have to differentiate that with respect to z, and I guess we'll use the product rule here. So differentiating the sine, you get a cosine. Using the chain rule, and differentiating the z, you'll get a 2yz coming out. So when you multiply 2yz times z squared, you get 2yz cubed. And then the other half of the product rule, differentiate z squared, you get 2z, leaving the sine term the same. So that's the fxyz partial derivative. Okay, let's see some applications of partial derivatives. So a lot of applications come in the form of differential equations. So some of you may be more or less familiar with differential equations. So essentially a differential equation is just an equation with derivatives in it. So in this case, we've got some function u that represents the temperature of a 1D object. So say a thin rod that has a temperature at different temperatures at different points in the rod, and u is a function of x and t. So x would be the position in the rod, and then t would be the time at which you're measuring the temperature. So u is really a function of position and time. So if u is a function of x and t, you can take derivatives with respect to x and derivatives with respect to t. And what the heat equation says is if you want to know how temperature behaves in a one-dimensional rod, it will follow, the temperature profile will be a solution to this equation, which is called the heat equation. So the first time derivative is equal to some constant times the second derivative in x in space. And k is some constant representing the thermal conductivity. So different media will have different values of k. And so my question isn't necessarily to solve this heat equation, but just to show that this function here actually solves the heat equation for k equal 1 and a any constant. Okay, so what is this? It's a function of space and time. Here's the t and there's the x, so it appears to be a function of x and t. And if we're going to show that it satisfies this equation, it means we take the t derivative of this and we take the second x derivative and set them equal to each other, and they should be equal. So let's start with the time derivative. This is the only place where t appears, so we're going to have a and cosine will essentially be just assumed constant. And if you differentiate the exponential, you get the exponential, but you have the chain rule as well, so you multiply by negative a squared right there. So there's the time derivative. All right, let's figure out these uxx, the second partial with respect to x. Okay, so the first partial with respect to x, we're just really differentiating cosine of ax, so that'll be negative a sine of ax times the a times the exponential term here, which is assumed constant. And then we differentiate that with respect to x again. Well, you'll differentiate sine, you'll get cosine, another a will come out, and so you get this. And then you just notice that in this case, if k equals 1, this is exactly equal to this. So ut equals uxx. So this equation here of x and t must somehow capture the way that temperature would behave in a rod. And I'm going to show you what that would look like. So first, here I've graphed this. Assume that the x-axis is the rod and the height is the temperature. So here we have maybe high temperature and here's low temperature. And what you would expect if this is a rod, that the high temperature, the energy from the high temperature areas would go down to the low, and the low would absorb some of the high temperatures. And so if we graph this function for different values of t, you see exactly that. The high temperatures become cooler and the low temperatures become warmer, until if you wait long enough, you essentially are just at a constant temperature of 0. So you get to an equilibrium. I've graphed that also in 3 dimensions. So over here, this would be where t is equal to 0. You can see the temperature up and down. And so this is your t-axis. As t increases, your rod is basically becoming constant. So this is the position, this is the time, and the height is representing the temperature. And you can see over time the heat just dissipates and averages out to 0. All right, let's try another one. You can try this for practice. So this is a 2D version of the heat equation. So instead of having a one-dimensional rod, we've now got a two-dimensional plate. So at each point in the plate, you've got an x and a y coordinate and a temperature associated to that point at every time. So really, this is a function of x, y, and t. X and y telling you where in the plate you are, t telling you what time you're at in the plate, and u giving you the temperature. So there's a two-dimensional version of the heat equation that looks like this. So it's again the time derivative and a kuxx we've seen before. And to get the second dimension added in, we just add in a kuyy. So sometimes the uxx and uyy show up so frequently summed together like this that it gets their own name called the Laplacian, with this little delta symbol here. So this is sometimes called the Laplacian of u. But this is an equation which would tell you how heat moves around in a two-dimensional plate. And one solution to this equation is this function right here. U of x, y, and t equals 1 over t e to the minus x squared plus y squared over 4t. And we're going to show that this solves the heat equation with k equal to 1. So to do that, I first need to find the time derivative with respect to u. So let's try that. In fact, maybe you want to do this for practice. Pause the video, try finding the t derivative, and then uxx, uyy, sum those together, see if it equals ut. All right. If you tried that, maybe we can see if you got it right. So what is ut? Well, differentiate 1 over t, you get negative 1 over t squared times the exponential. Now differentiate the exponential, you get 1 over t times the exponential times the derivative of the inside, which is going to be, well, it's essentially a negative 1 over t, so that's going to be 1 over t squared, and the other terms are constant, and there's already a t there, so you end up with a t cubed in the denominator. So that's the time derivative right there. All right, let's work on this uxx term. So let's start with ux. 1 over t is just constant, so we just differentiate the exponential. We get that times the derivative of the inside, which is just going to be negative 2x over 4t. This is held constant, so we only differentiate the x term here to get that. And then, well, we differentiate it, but we get 0 essentially. Take the derivative of this now, we'll have to use the product rule. So if we differentiate this term, we'll just get the same thing we had before, so we'll get another copy of negative 2x over 4t, so it'll be squared now. And then we differentiate this with the product rule, the x will just go away and we'll get negative 2 over 4t. And there's really no difference between x and y, so we should get the same thing when we do uyy, except there'll be an x here, or a y here instead of an x. So that's what this says right here. And if it works, the uxx plus uyy should equal ut if we did our calculations correctly. So let's try that. So here's the 4 terms summed together, and they should equal this if we did our calculations right. So let's check. Let's start with these terms right here. Okay, so all 4 terms have this exponential term, and these terms have the exponential. So in some sense we could factor that out, and what we really need is to end up with this and this as the coefficients. So here we're getting a t squared, and here we have a t squared. It's negative, which is good. And here we have basically 1/2 and another 1/2. Of course, 1/2 plus 1/2 is 1. So that these terms here give us this. And so these terms here should give us this. So we already factored out the exponential. How many t's are in the denominator? 1, 2, 3. Okay, 1, 2, 3. So that's good. And there's an x squared and a y squared in the numerator, so x squared plus y squared. And then in the denominator, well, this is 1/2 squared, so that's 4. 1/2 squared, so that's 4. So that factors out as well, so we get the 4 there. All right, so this function here solves the 2D heat equation, and we can actually see that in action as well. So I've graphed the function for different values of t. This would be a lot of heat kind of right here along the u-axis, but then not very much heat over here. So the temperature is low over here and high right at 0. And what happens as we advance time? Well, it seems like the temperature goes down pretty quickly. I'll maybe try to do that a little bit more slowly. But there, it's already going down. So let me zoom in a little bit. And then we can advance time again. So you see the heat is going down as the heat spreads out to the rest of the domain. And probably over here, maybe the temperature is coming up a little bit as it gains heat. But that big spike in the middle over time goes down nearly to 0. Nearly to 0. And you can actually see that from the equation, because as time increases, you're having a 1 over t here, and this will be an exponential term, but it's negative, and so for positive time, this is going to be some negative exponential. So it would make sense that this would actually be less than 1 as well, and this is shrinking. So you can see it sort of makes sense that the temperature would be going down everywhere as well. All right. So a couple other things that where you might think about some partial derivatives. So if you look at cooling towers of nuclear reactors, they actually satisfy, they're usually built along hyperboloids, I guess, which would have this equation here. We actually saw hyperboloids earlier when we studied quadric surfaces. But what's interesting here is the shape is structurally stronger than a cone or a cylinder. It takes less material to build, and it actually maximizes the natural upward draft of the hot air without the need of fans. So you can think about taking partial derivatives of something like a hyperboloid as well, and so there's some applications there as well in terms of what kind of curves get built and why, and what kind of structures should we use for achieving a particular purpose. Let's finish with a little bit of theory here, not too much, but just a sense of some of the definitions that go along with derivatives. So we've seen before continuous functions are good. What's even better is differentiable functions. So most of the functions you know the names for are continuous. Okay, not every single function you can write down as a continuous function, but for the most part in this course we're going to be interested in continuous functions. It's even better if the function is differentiable. We usually call differentiable functions smooth. Differentiability has some notion of there not being corners in functions. Okay, so that's sort of where the name smooth comes from. In other words, they shouldn't have jumps, corners, creases, or cusps. Because those places would give you non-differentiability. So here's kind of an interesting question. Let's say I have a bag that has all of the possible continuous functions in the world, and I reach in and pull out a function at random. What are the chances that my function is differentiable? So you might want to think about this. So in some sense, of all of the continuous functions, how many of them are differentiable? About half, a third, all of them? And why this question is so interesting is you can prove mathematically, of course not in this course, but in an advanced course, you can prove that the probability of selecting a differentiable function given a continuous function is actually 0. So most continuous functions are not differentiable anywhere, actually, which is absolutely baffling because so many of the functions we deal with and that are interesting and that solve problems are actually differentiable. And so there's something really sort of mind-boggling going on here, the difference between continuous and differentiable. This is a much stronger condition. All right, so it's really nice to have differentiable functions. What's so cool is that most of the functions we need to solve the problems we care about are differentiable. And so there's something interesting, although in some advanced physics classes, maybe Brownian motion, you can talk about some continuous but not differentiable functions. Okay, so a little bit more about differentiability. So in one variable, differentiable means you can place a tangent line on the function at every point. So in two variables, differentiable means you could place a unique tangent plane on the function at every point. So that's sort of a natural extension of the notion of differentiability to 2D functions. So essentially, we want something that's smooth like this, not cuspy like that. So this function is probably differentiable everywhere except for at that cusp, but not there. Whereas this one looks like it's differentiable even there at 0, 0, and smooth everywhere else. And you can imagine putting a tangent plane here, but I could put lots of different tangent planes here that would only touch the graph once, but wouldn't. How do you get the notion of sort of tangentness when you're at a cusp? All right, and what's nice is we have this theorem. We don't really have to think about differentiability broadly because if a function has partial derivatives, fx and fxy, that are continuous, then f is differentiable. So partial derivatives which are continuous on a region means the function is differentiable. So if you wanted to know whether you can build a tangent plane on every point on a function, all you have to do is figure out whether you can take the x and y partial derivatives. So maybe you're wondering, well, maybe we can use the partial derivatives to find the tangent plane just like you use the derivative to find the tangent line in Calculus 1, and that's where we'll be heading later on in the course. All right, so that's all I have for you. We'll see you next time.